excellence in highway transportation is a feature Americans have been conditioned to expect. Each year, Americans travel over 1.5 trillion miles on U.S. roads, and 1/2 of this travel takes place on the interstate and primary systems. Portland cement concrete is one of the materials used to construct durable pavements for the increasingly mobile public. Thousands of miles of Portland cement concrete pavements are now part of the interstate highway system, which stretches across America, providing a fast and efficient means of travel for millions of motorists. As the years pass, deterioration has taken its toll. The forces of nature, together with the constant pounding of heavy traffic, eventually cause cracking, faulting, and spalling in concrete pavements. These conditions create safety hazards for motorists and can lead to premature failure of the pavement. This is why today we are faced with a new challenge, a challenge not as glamorous as building the highway system, but one that is of equal importance, the challenge to maintain, rehabilitate, and reconstruct the system. In recent years, dollars for these activities have not kept pace with the need for highway improvements. Inflation has eroded buying power, and many highways have reached their design life. The result of this is the inability to provide a high-quality highway system. The 1982 Surface Transportation Act has taken the first step toward solving the problem. However, the needs still far exceed the means. For this reason, the importance of following good engineering practices in developing pavement rehabilitation projects is essential if the goal of getting the best return possible for the money expended is to be attained. A step-by-step process should be followed to evaluate the existing pavement and determine the proper rehabilitation techniques. First, available project information should be obtained. It should include as-built data, traffic, past maintenance and rehabilitation, accidents, performance history, climatic data, and such. Next, the existing condition of the pavement and the cause of any distress should be determined. This information is used to develop feasible restoration alternatives, along with engineering and economic evaluations. Based on these evaluations, the best rehabilitation alternative is selected and designed. These alternatives may include recycling, bonded and unbonded overlays, or restoration techniques. Finally, follow-up reviews to check on the performance of the rehabilitation techniques need to be conducted. If these steps are followed in the design of pavement restoration projects, pavement performance will be greatly improved. While steps 1 and 2 are fairly self-explanatory, step 3 is perhaps the most difficult and challenging of the process. One common cause of pavement distress is the displacement of support material from beneath the concrete slabs. Water, which may be either groundwater or surface water seeping in through joints or cracks in the pavement, tends to weaken and erode the foundation soil. Heavy traffic passing over the pavement causes a pumping action, which accelerates the process. The loss or displacement of support material from beneath the slabs causes a stair-step effect, which is called faulting on the pavement surface. Faulting most often occurs at transverse joints and is associated with a loss of load transfer across the joints. Severe loss of foundation soil can lead to cracking of individual slabs, either at the corners or running the entire length of the slab. A survey should be conducted to determine the location of voids beneath the concrete pavement. One method of void detection is to use the falling weight deflectometer. This trailer-mounted device exerts a dynamic load on the pavement. First, a load plate is lowered onto the roadway. Next, a weight package is raised, then dropped on a dampening system. Each testing sequence normally consists of 3 progressively higher drops. The resulting pavement deflection is measured by seismic deflection transducers, spaced at intervals in front of the loading plate. A computer in the cab of the tow vehicle programs the test sequence and records extensive data during the testing procedure. A 3-drop test sequence is conducted on each side of the transverse joint. Other similar automated devices, such as the Dynaflex and Road Rater, have been used for void detection. Another means for determining void locations is to use deflection gauges. The one shown is a shop-built deflection measuring device. The instrument is placed on the pavement so that one deflection gauge is located on each side of the joint. A truck containing a known wheel load is then moved forward and stopped, with the rear axle slightly behind the joint. Technicians note any deflection on the indicator dials. The truck then moves on across the joint and stops, while technicians again read both dials. Correlation should be made between a Benkelman beam and the shop-built deflection device to establish its accuracy before beginning the project. Once all this information is gathered and analyzed, steps 4 and 5 of the design process can begin. If deterioration has reached advanced stages, rehabilitation may require total removal and recycling of the concrete pavement. If distress is limited to short sections of pavement or isolated slabs within a section of roadway, concrete pavement restoration procedures may be faster and more economical than total reconstruction. A 7-part restoration program has been developed which can be used to repair various types of distress in concrete pavements. The 7 concrete pavement restoration activities include full-depth slab repair, slab stabilization, partial depth slab repair, the restoration of load transfer between slabs, diamond grinding, resealing of joints and cracks, and shoulder restoration. The restoration activities required to repair a given section of roadway will vary, depending on the types of distress which are present. Once concrete pavement restoration has been chosen as the rehabilitation alternative, the work begins with full-depth slab repair. Diamond blade concrete saws are used to make full-depth cuts around the perimeter and across the slabs, so that sections of the slabs can be lifted from the roadway. 3 successively deeper cuts are made until the slab has been cut to its full depth. Sawing and lifting out the slabs is faster than braking methods and results in less damage to the existing subbase material. Once each slab has been cut, anchor holes are drilled in each section. Bolts or lifting wedges are driven into the concrete and fitted with hardware for the lifting operation. A crane or front-end loader can be used to remove the cut sections of concrete from the roadway. The removal operation proceeds rapidly, and only minor handwork is required to ready the subbase material for new concrete. Of prime importance in the repair process is the replacement of load transfer between slabs. The use of steel dowel bars is the best method of restoring load transfer when individual concrete slabs must be replaced. Holes for the dowel bars are drilled with a frame-mounted power drill. These drills can be single drills or drills mounted in tandem. Care must be used to assure proper horizontal and vertical alignment of the dowels. Once the holes are drilled, they are blown clean, and a stiff epoxy or non-shrink grout is placed in the back of each drill hole. Cardboard tubes provide an excellent means of placing the grout well into the back of the hole. Dowel bars are then inserted into the drill holes, forcing the epoxy or grout forward and completely sealing the dowel in place. The dowel bars are typically 1 1/4 inches in diameter and 18 inches long. After the dowels and/or tie bars are installed, standard Portland cement concrete is placed. If required for early opening to traffic, a high early strength PCC can be used. Standard quality control tests such as slump and air entrainment measurements are performed on the ready-mix concrete. In addition, beams and cylinders can be molded for strength testing purposes. A power screed should be used to strike off the newly placed concrete. Final finishing involves the use of hand tools. A burlap drag or broom finish can be used to texture the surface. When finished, a coat of white pigmented curing compound is applied to the surface of the new slab. In some areas, several slabs may need to be replaced. A large crack in the pavement may require the replacement of 2 or more consecutive slabs. Again, the slabs are sawed full depth with diamond blade concrete saws, then removed by lifting the pieces out with a front-end loader. A standard dowel basket is placed in the area where the transverse joints are to be reestablished. Portland cement concrete is then placed in a continuous pour through the joints. Slab repairs are generally open to traffic in 3 to 4 days. When required, due to traffic control restrictions, slab repair operations can be completed by noon on the same day they are begun. The new slabs are reopened to traffic before dark on the same day they are placed when high early strength Portland cement concrete is used. Once the slab repairs have been completed, holes are drilled for the slab stabilization operation. The holes are drilled entirely through the pavement, through the subbase, and about 3 inches into the subgrade. Down pressure on the drill must be minimized to prevent breakout at the bottom of the slabs. A flowable grout is pumped through the holes to fill the voids under the pavement. The stabilization grout typically used today is produced from 1 part Portland cement, 3 parts fly ash, and sufficient water to produce the desired flow rate. Fly ash is a relatively inexpensive pozzolan produced by the combustion of powdered coal. This fine powder-like material is composed largely of silt-sized, round particles. The spherical shape of the particles creates a ball-bearing effect, which enhances the flow properties of the grout. Class C fly ash, which is widely available in many parts of the country, reacts with water to form a cement-like material. Thus, grout produced with Class C fly ash will harden to form a strong, incompressible, and non-erodible material. A colloidal mixer is used to produce the stabilizing grout. The high-speed mixer operates in the range of 800 to 2,000 revolutions per minute and produces a mix which will stay in suspension and resist dilution by free water in the voids. A positive displacement cement injection pump is used to place the grout. The injection nozzle is equipped with an expanding rubber seal. During the pumping process, care should be taken to avoid lifting the slabs. The purpose of stabilization is merely to stabilize the slabs by filling the voids, and not to raise the slabs. For this reason, plugging the injection holes during the grouting operation is not recommended. 3 different grouting hole patterns have typically been used. The first uses 3 holes per slab, the second 4 holes per slab, and the third 5 holes per slab. Pumping at each joint continues until grout is visible escaping through an adjacent hole. Pumping is also stopped anytime grout begins escaping through joints in the pavement or movement of the slab is detected. A device such as the Benkelman beam must be used to monitor uplift during slab stabilization operations. Other requirements for suspending of pumping from any hole are indication of slab lift with a maximum 1/8 inch allowable or a rapid increase in pumping pressure with a maximum allowable of 100 psi. The stabilized slab should again be checked for pavement deflection. This process is called proof rolling and is used to determine the effectiveness of the stabilizing operation. The falling weight deflectometer and the static load measuring device can be used for proof rolling purposes. The next step in the process is spall repair. Spalling occurs when incompressible materials become lodged in open transverse joints. During hot weather, the concrete surface near the incompressible object breaks due to the tremendous expansion pressure created by the closing joint. Spalls usually start as delaminations at the joint. Each joint on the project should be sounded to find these delaminations so repairs can be made before the actual spalls appear. To repair the spalled or delaminated joints, the area around the damage is sawed to a depth of 1/2 to 2 inches, then chipped out with small 30-pound maximum jackhammers or small rotomill machines. The hole is then cleaned with sandblasting equipment to ensure good bonding of the patching material. A neat cement, sand cement, or epoxy bonding grout is brushed into the surface and the concrete placed. Before any concrete is placed in the patch, a compressible joint material should be placed in any existing joints, transverse and longitudinal. This material should extend the full depth of the patch down into the existing joint. This will prevent compression failures in the future when the slabs expand. The repair area is now ready to receive the patching material. A high early strength Portland cement concrete can be used in the spalls when required due to traffic restrictions. Small spud vibrators should be used to consolidate the concrete. Finally, the surface is finished and cured. Curing will be the same as for full-depth repairs. Once repairs have been made to the pavement, consideration should be given to restoring load transfer at the existing joints and cracks. 2 different types of retrofit load transfer devices have been installed with some success. Dowel bar retrofit begins with the use of a concrete saw equipped with 3 diamond blades, which cut slots for the installation. The slots are cut to sufficient depth to allow placement of the dowels at mid-depth of the slab. After cutting, the concrete in the slots is chipped out with a jackhammer, then cleaned by sandblasting and compressed air. Each dowel is mounted on chairs and fitted with an expansion cap on one end, which allows the bars to slide as the slabs expand or contract. The bars are placed in the slots along with a piece of compressible insulating material which forms the contraction joint. Patching in the slots for the dowel bars is the same as a spall repair. A second type of load transfer device is also available. This experimental unit, which is called a double V load transfer device, is designed to be installed in a standard 6-inch core hole. Installation begins by drilling core holes at the joint. A pattern of 3 or 4 holes per joint is used, with 2 holes in the outside wheel path and 1 or 2 in the inside wheel path. The structural integrity and stability of the pavement has now been restored by full and partial depth repairs and slab stabilization. Pavement distress such as faulting, minor wheel ruts, and poor skid resistance can now be repaired by the use of diamond grinding. Diamond grinding requires heavy, specially designed equipment, which uses diamond saw blades gang-mounted on a cutting head. There can be anywhere from 50 to 60 blades per foot on the 38-inch cutting head, depending on the hardness of the aggregate. An accompanying tanker truck is connected to the pavement grinder and provides cooling water for the cutting head. A vacuum system surrounding the head picks up most of the concrete slurry. If required, the slurry can be collected and disposed of off-site. The pavement grinder acts similar to a wood plane. The front wheels pass over the bump and the cutting head shaves the bump. In this way, faults and bumps are removed, leaving a smooth riding roadway. The diamond grinding process is impact-free and does not damage joints. Grinding equipment typically operates against traffic. This is done in order to cut into faulted transverse joints, which allows for a smoother ride on the pavement and more efficient operation of the grinder. However, this is not generally noticeable to the oncoming traffic because of the machine's slow rate of travel. Additionally, the tanker truck should be placed in front of the grinder, facing the direction of travel. The resulting pavement surface after grinding has a corduroy appearance, which leaves a skid-resistant, smooth-riding pavement. At this stage, one of the most important steps of the restoration project is undertaken: joint and crack sealing. Properly sealed joints and cracks will prevent water and incompressible materials from getting down into the joints. This minimizes spalling, pumping, faulting, and blow-ups. There is a 4-step process to reseal joints properly. 1. Remove the old sealant. 2. Cut a new reservoir. 3. Clean the joint. And 4. Place the new sealant. First, any old sealant in the joint is removed by plowing or sawing. In plowing, a plow blade mounted on a tractor is lowered into the joint where it can effectively pull out the old sealant. In cases where the existing joints are narrow, the old sealant can be removed during the sawing of a new reservoir. When the old sealant has been removed, the joints are resawed using conventional sawing equipment with dual blades and spacers to obtain the proper shape factor. The shape factor will vary depending on the original design, joint spacing, and the type of sealant being used. The sealant manufacturer's recommendations should be checked when determining the proper shape factor. Immediately following sawing, the joint should be flushed with water to remove saw slurry and foreign material. When dry, the joints are sandblasted to remove any saw residue remaining on the joint face. The joint is then blown out with air to remove sand and dust. A clean joint is critical to provide a good sealant bond. A quick check is to rub a finger along the joint face. When the joints have been cleaned and are completely dry, a backer rod is placed in the reservoir. This assures that the proper depth of sealant is installed and prevents the sealant from sticking to the bottom of the joint, which causes higher stresses in the sealant that can lead to failure. With the backer rod installed, the joint sealant is placed in the joint. The joint should be filled from the bottom up. This helps prevent overfilling of the joint. The surface of the sealant should be kept 1/4 to 3/8 of an inch below the surface of the pavement. Random cracks are repaired in the same manner as joints. A random crack saw with an 8-inch diamond blade is used to produce a sealant reservoir. This is done on working cracks. Hairline cracks that are non-working should be left alone. The final step in concrete pavement restoration is shoulder repair. As a minimum, any existing bituminous shoulder should be removed and replaced. Once the shoulder is replaced, the joint between the shoulder and the pavement is sealed. It is estimated that 80% of the surface water that gets under the pavement enters through the shoulder joint. A reservoir is cut into the shoulder along the edge of the pavement and flushed with water. When the joint is dry, it is filled with a hot-poured sealant. Portland cement concrete pavement restoration is another design alternative which transportation engineers can use to repair our highways. CPR can restore structural integrity, ride quality, and skid resistance to the concrete pavement. When used in the proper place at the proper time, Portland cement concrete pavement restoration is a cost-effective process that will extend the life of our nation's concrete roads and highways.